In Noise, a book by Nobel Prize winner Daniel Kahneman, along with Olivier Sibony and Cass Sunstein, they claim that while correlation does not imply causation, causation does imply correlation. In episode 1 of this series, I argued that the first claim is false. Correlation, understood as genuine probabilistic dependence, does imply the existence of a causal explanation. But what about the second claim? Does causation imply correlation? Hello, and welcome to Causal Foundations. I'm Naftali Weinberger, a philosopher of science who's been researching causal models for over a decade. In this series, I introduce foundational concepts from causal inference in videos of approximately 10 minutes. Today's episode will cover the causal faithfulness condition. Informally, the causal faithfulness condition says that causation does imply correlation, or equivalently, that a lack of correlation implies a lack of causation. To make this more precise, we need the notion of deseparation, which I cover in episode 2 and reviewed in the last episode. There I discussed the causal Markov condition, which states that if x and y are deseparated by z in the causal graph, or DAG, then they're probabilistically independent in the associated probability distribution. In contrast, the causal faithfulness condition, or faithfulness if you're into the whole brevity thing, states that if x and y are probabilistically independent conditional on z, then they're deseparated by z in the true causal graph. But this is basically a precise way of saying no correlation implies no causation. To better understand faithfulness, let's see how it can fail. Consider a generic causal model in which x influences y both indirectly via z and also directly via omitted variables. If these two causal paths exert equal and opposite influences, then x will have no net effect on y, and x and y will be uncorrelated, despite x's causing y. More precisely, we can give structural equations indicating how each variable responds to interventions on its causes. Here, x influences z by linear coefficient alpha, and y depends on z and x by coefficients beta and gamma. Cancellation occurs exactly when alpha times beta is equal to negative gamma. There's a standard argument for why we shouldn't expect such cancellations. It begins from the premise that the set of parameter values that cancel is infinitesimally small, or measure zero, compared to the set of all parameter values. This is illustrated by the fact that the canceling set is a one-dimensional line in the two-dimensional space of combinations. The argument concludes from this that it's vanishingly improbable that cancellation will occur. What's interesting about this argument is that it moves from a measure-theoretic claim about the size of the set of canceling parameters to a probabilistic one about how often they cancel. I'll soon devote a whole episode to the measure zero argument, since the type of reasoning involved pops up in strange places, including in arguments that we're living in a simulation. For now, 2 points will suffice. First, there are many cases where faithfulness fails by design. To give an example due to Dan Steele, suppose a city improves the roads, which would lower traffic fatalities, if not for the fact that people are more likely to speed and get into accidents. The city then hires more police to discourage speeding, but only to the point necessary to offset the rise in fatalities. If they succeed, then there will be no correlation between road improvements and fatalities. Such examples can be multiplied in policy domains such as economics. Similar examples arise in homeostatic systems in biology and control feedback systems in engineering, though modeling these is more complicated. Second, even if the argument showed that the set of exact cancellations has probability 0, it would not follow that near cancellations do. And given finite data, we won't be able to distinguish exact cancellations from arbitrarily close ones. Many people seem to think that faithfulness just means no cancellation, But there are other ways that faithfulness can fail. Suppose that X causes Y and Y causes Z, and the causal relationships are deterministic. By this I mean that the structural equations contain no random error terms. Because the value of X determines the values of Y and Z, conditioning on X is operationally the same thing as conditioning on Y and Z as well. Since Y provides no further information about Z conditional on X, Y and Z are probabilistically independent conditional on X, even though they're deconnected by the causal arrow. A further counterexample to faithfulness involves a failure of transitivity. Michael McDermott gives an example in which a terrorist plans to set off a bomb with his right hand. A dog bites his right thumb, leading him to set off the bomb with his left hand. In this example, the dog bite leads the terrorist to set off the bomb with his left as opposed to his right hand, and his setting off the bomb leads it to explode. But the dog bite is uncorrelated with the bomb exploding, despite the causal path. Finally, consider a bell that goes off if two fair coins both land heads or both land tails. Each coin influences the bell, but learning that one coin landed heads won't change the probability that it rings from 50%. This failure results from all of the conditional and unconditional probabilities being exactly 0.5. We see that cancellation is far from the only way that faithfulness can fail, but there is a way in which cases involving cancellation are unique. Consider again the causal triangle we've seen repeatedly. If there's cancellation, then X and Y will be unconditionally probabilistically independent, but dependent conditional on Z. If one assumed faithfulness, one would infer the collider structure on the right, since that would account for this pattern of independencies. Zhizhi Zhang and Peter Spirtes call this an undetectable failure of faithfulness, since there is a faithful model which is false, and nothing in the distribution indicates that it's false. Zhang and Spirtes realized that in some cases, no model satisfies faithfulness. Such failures are detectable, in the sense that one can use principles weaker than faithfulness to learn that no model can satisfy faithfulness, and build algorithms that exploit this. All of the examples on the previous two slides are detectable failures. Moreover, even some cancellations are detectable. For instance, if the canceling indirect path contains two mediators, then there will be no model that's able to account for all of the observed independence relationships. In fact, it turns out that all undetectable failures of faithfulness involve a canceling triangle with a single mediator. The fact that it's possible for there to be no model satisfying faithfulness suggests that it's in some sense too strong. Causal discovery algorithms seek to reduce the set of candidate causal hypotheses, and in some cases, faithfulness eliminates all of them. There are several weaker principles that play a similar role. The one I'll discuss now is called minimality, and I'm specifically referring to the version formulated by Spirtes, Glimor, and Shyness. We say that a graph is not minimal if it's possible to remove a causal arrow and for the DAG to still satisfy the causal Markov condition. For instance, if we consider the triangle graph, along with a distribution in which Z and Y are probabilistically independent given X, this is not minimal, since one could remove the arrow from Z to Y, and the graph would still satisfy the causal Markov condition. So minimality says not to choose the DAG on the left. Minimality is a very weak condition, since it only compares graphs in which one is derived by removing arrows from the other. Returning to the canceling triangle graph from the last slide and its faithful counterpart, neither of these models is minimal with respect to the other. Since the arrows between X and Z go in different directions, minimality can't compare them. So minimality is rather weak, though there do exist several principles that are stronger than minimality, but weaker than faithfulness. Just because faithfulness isn't always true, doesn't mean that it can't be a reasonable assumption in certain domains, and adopting it greatly facilitates causal inference by narrowing down the set of candidate causal DAGs. So there's a lot more to say on the practical side. But as a general principle, we can definitively say that causation does not imply correlation. Kahneman and friends get things exactly backwards when they implicitly reject the causal Markov condition and accept faithfulness. While the causal Markov condition is an indispensable bridge principle for causal inference, whether faithfulness is justified is more of a practical matter, of which heuristics help simplify causal inference. Thank you for listening. For further reading, you can always check out Causation, Prediction, and Search, as well as this additional article by Daniel Steele on the measure zero argument. The last article is a reference for detectable versus undetectable failures of faithfulness.